Okay, sure.
Yeah, okay, yeah. Let's see.
So should we start? Wait for me few more minutes.
No, we're going to start. Yeah, we can. I think we can start now. Yeah, yeah, we can start now.
Okay.
Right. Yeah. Okay. So welcome to this week's series on the One World Mind seminar. It is our pleasure to have with us Professor Ji Hui to speak with us today. So let me introduce Professor Ji Hui. It's also my colleague. He's a professor at the Department of Mathematics at the National University of Singapore. Ji Hui is an expert in the imaging sciences. His research interests span a broad range of topics relating to imaging tasks. I think started from like wavelets in earlier days and more recently into deep learning. Ji Hui serves as an associate editor on the SIAM Journal on Imaging Sciences, as well as sits on the editorial board of the AIMS Journal on Inverse Problems in Imaging. Within NUS, he also serves as the director of the master's program on the data science and machine learning. Ji Hui is a colleague of mine. I found him to be a really excellent teacher. One learned a lot about how the field of imaging sciences has evolved over the decades in a nice, coherent, exciting manner. And that's, of course, for these reasons, I think I look forward to hearing from him today. So great pleasure to have him here. So Ji Hui, the floor is yours.
All right. Thank you. Thank you, Yunsheng. Very nice introduction, and it's great to have the chance to share some research works with the colleagues in this wonderful One World Mind seminar. All right, so today we will discuss what we have been done in the last 5 years on self-supervised deep learning for inverse problem related to imaging science. So if you look at what is the inverse problem in the imaging, essentially when you do some imaging task, you have a forward process. So you can collect some measurements on some physical quantity, and this physical quantity X can be visualized as 2D or 3D images. So basically, then the so-called inverse problem means you try to get this image you are interested from the measurement. So basically, suppose you have a measurement which can be modeled by the forward process applied on the image X. You try to get them back. So you try to estimate X from the Y. So when usually this inversion process is asked you to solve air-conditioned or air-posed problems. Air conditioning means if you directly reverse it, you actually will amplify the noise. And air-posedness here refers to that the solution is not unique. That means measurements are not enough. So here are some examples. In medicine, you have the image reconstruction for CT, especially low-dose CT. So you have a CT scanner, you collect measurements of so-called sinogram, which characterize some structure of your patient's internal organs. Then your goal is try to construct an image which can show the internal organs of the patient, which actually require you to solve an ear-posed linear system, which means you actually, the matrix A is not enough, such that you have more unknowns than the equations. So you have many solutions. Another one is called phase retrieval in science or engineering. Here is examples of X-ray diffraction images. Basically, if you have some structures, you try to use the X-ray diffraction imaging techniques to capture the data, and the data you captured indeed can be modeled as the magnitude of the Fourier transform of the image. But you only have the magnitude of the Fourier transform, right? So you don't have the phase. Therefore, you have severe solution ambiguities because you are missing the phase. You need both phase and the magnitude to reconstruct the image, right? So this is a nonlinear ear-pulse problem. And the other one is happens in our daily life is if you take pictures using your phone, and if your phone is not steady, there is some certain amount of camera shake during the shutter time, then the image will look blurry. I think many people have seen such kind of phenomena, right? When you take pictures using your phone. So in this case, this problem often can be modeled as a nonlinear inverse problem. To be exact, is actually bilinear problem. So you can model the blurring process as a convolution process. So the blurred image Y indeed can be viewed as you apply some smoothing convolutional kernel on the target clear image. But here we don't know what is the convolutional kernel. That is, you have to estimate both the image X and the smoothing kernel P from Y. It's more like you have some multiplication. You have to guess who is multiply who to get the things you see. Okay, so here is certainly a ear-pulse problem, and it is a bilinear inverse problem. Also today, these are the applications we're going to targeting, and so today our talk will go through 3 parts. First, I will give you a very quick review on the representative approach to solve this inverse problem in the past, including the regularization, Bayesian inference, and supervised deep learning. Then I will move to the main part of today's talk, the self-supervised learning, and we have two approaches. First is design the self-supervised loose functions so that it enable to teach the network to do accurate prediction without knowing the truth. Particularly, we are into so-called R2R and its extension. Then I will move to the so-called self-supervised approximate MMSE estimator for solving inverse problem. Here, MMSE refers to the minimum mean square error estimator. All right. So okay, let's give a quick review on what the typical way to solve an ear-pulse linear inverse problem, not restrict to linear. Okay, if you consider an ear-pulse inverse problem, then the regularization method probably is the most renowned approach to solve it. Basically, it tries to address this ear-pulseness by impose some prior to restrict the range of the estimation. So the sparsity prior has been like the most famous image prior widely used in the last 2 decades. So the idea is that you assume that under some transform or under certain domain, the coefficient of image will exhibit the behavior that many of the coefficients will be 0 or close to 0. So the representative transform will be the gradient or the wavelet transform. All right. So, but try to impose these prior will lead to the so-called L1 norm latent regularization. So try to enforce such a sparsity prior on the estimator. Then you will have the L1 norm latent regularization method. The most famous one will be the TV. Right. This has been like the most famous one in the last 2 decades before deep learning. All right. So, but we actually in parallel we have the community in the statics, right? So have the similar things called Bayesian inference. So for Bayesian inference, usually an image is viewed as one instance drawn from some underlying distribution P of X. And then you have the ML estimator, which try to maximize the conditional probability of Y given X. But if you consider Gaussian white noise, then it comes to solve a problem which actually is a fitting term. And this certainly cannot address the solution ambiguity, right? So therefore, the consecutively people will switch to the MAP estimator, maximum posterior estimator, which actually try to maximize the conditional probability of X given Y. So if you apply the Bayesian rules, somehow you can switch them back to the ML term together with the log P of X. So if you consider Gaussian white noise, we actually have one additional term in comparison to the ML estimator. That is, you try to also minimize the log, you try to minimize the negative logarithm of P of X. So we also call this P of X is a prior. It's just expressed in the form of the distribution. So clearly, actually, this is well known, all right? So the regularization and the MAP actually come to the same thing if they try to define the similar priors. If you look at the regularization method, this is a target function they try to minimize to get estimator, and this is the MAP estimator. And they actually minimizing things all related to the priors. Just one is expressed in the deterministic way, one is expressed in terms of the distribution. So if you consider the PV regularization and MAP estimator, we actually just saying if we assume the X follows a Laplace distribution defined on its gradient, we actually come to the same solutions. So there's no difference between MAP estimator and the regularization, just different language. However, when deep learning comes in, things change. So deep learning certainly is a game changer for many things, including the solving inverse problem, right? So deep learning means you try to learn with a deep neural network, which is actually a very highly nonlinear function with many parameters. Right? Here, the parameters usually refers to the weights of the network. So the high nonlinearity of the deep neural network comes from the fact that it's a chain. It's actually the concatenation of many simple nonlinear layers, and the composite of these many nonlinear layers actually can lead to very sophisticated nonlinear function. The other one is we have to pay attention that often this model is over-parametrized. They actually come, especially in the when you solve an inverse problem in imaging, usually the parameters of the model go to the level of millions. All right. So now, if we go back to consider solving an inverse problem, okay, then deep learning directly just learns the inverse process. All right. Just assume the deep neural network is complex enough; it can express such inverse process. Then they just learn, which means they just find the weight, the beta, the network weight, so that it can train the network so that it can simulate the inverse process. And this, how well it's simulated is in terms of their prediction error on the training data. Well, the things change here because the supervised deep learning is no longer a MAP estimator we often see in the past. It's actually a MMSE estimator, the minimum mean square error estimator. Because it's quite clear. So because you try to train a network so that it can predict the truth with minimum mean square error, right? So in other words, this indeed is actually trying to approximate the expectation error, right? This exactly is the minimum mean square error, right? So the deep learning, supervised deep learning is actually trying to learn MMSE estimator. Here we're going to use another definition. This minimum mean square error, MMSE estimator indeed is the conditional expectation equivalent. So certainly, if you look at the MAP and MSE, they have a different result. One is aiming for get the best estimator for a particular point, but MSE try to get the estimator which is best in average. All right, so before deep learning, actually, MSE is hardly used for image reconstruction. Why? It have two reasons. So first is MSE suffer from the same issue as MAP, right? How to define an accurate prior for the image. That is always there because you still have to rely on the Bayesian rules. So it does not introduce anything which can solve such a challenge. Secondly, MSE is actually has a very high computational cost. Remember, because for the MS estimator, we actually try to calculate this integral conditional mean, and we have usually people just using the Monte Carlo method to calculate such integral, right? However, the thing is that different from the classic Monte Carlo, we are handling very high-dimensional Monte Carlo simulation because an image typically going to have millions of pixels, which means you have to run the Monte Carlo simulation in the dimension in a space with millions, whose dimension is million, right? It's a super challenge task for the Monte Carlo simulation. So it's hardly used in the past. But however, in the deep learning, I mean, super deep learning is actually trying to do that. But it solves the problem in the sense that because it bypass to define the prior P of X, just train inverse process, then you can collect enough data. Secondly, computer cost is still there, but with this rapid advance of the GPUs and efficient deep learning algorithm, this one people think is okay now. All right, so however, while it looks good, but they have issues for super deep learning, that is data dependency. So if you want the super deep learning working well, you need a great amount of data and of high quality data. So in some sense, super deep learning is only work well for either of the case. Either you actually can collect a great amount of data, which cover all the characteristic of the target data, or you actually can get many data which actually highly correlated to the data you want to process. All right, these two cases are actually very hard to meet for certain applications. For example, in the medicine, it's not easy to collect or to use the true medical images of patients, right? In the science, that because your goal in science, you try to discover the structure which is not presented in the existing data set. You try to discover something new, but super deep learning will give you something it see often. So there's a bias. So here, that's certainly the interest to do this data set free deep learning. So where we define the super deep learning is that you try to learn with zero sample to predict the missing piece from the partial piece you have. And how to do it is try to leveraging the structure of the data cell. If you look at the configuration of supervised learning and unsupervised learning or self-supervised learning, the difference comes from the training data set. In the supervised learning, you actually have both Y and X. Okay, but however, in the self-supervised learning, sometimes you have set of measurements only, sometimes you have nothing. They all have to get some deep learning model to predict. Okay, so certainly the main challenge is overfitting, right? Because you don't have choose. You don't know how to teach the network to make a correct prediction without giving the truth. That's very challenging. And for example, if you look at image denoising, this is a very simple task. That is, you have choose image xi, but you only have its noisy version. But if you only have y with you, right? What you can do? If suppose you want to train a network to predict y with input y, so the network will just go to do nothing. It just converges to the identity map because it gives you least error, which means because your measurement of the prediction error is not right. Why it's not right? Because you don't have choose. So okay, so now let's come to the first question. So let's start with this very basic question: image denoising. This is actually this image denoising itself is important, and it actually gives very hints when you design a solver to a general inverse problem. So if you look at the difference between supervised learning and unsupervised learning or self-supervised learning, what's the difference is the training data. One is you have choose image xk. The other is you only have measurement yk. Right? So the main challenge is actually what you don't have here is loss function. You don't have loss. If you don't have loss function, you don't know how to teach the network to make prediction, which is accurate, right? So here, if for the main task in the self-supervised learning is how you can define a loss function to measure the prediction error, so that the network you train can make accurate prediction. So we have a solution called recorruption to recorruption. The idea is simple. The usage is how to use it is also simple, but it's very it has solid foundation. So if we consider a single measurement of x, which is noise, so we have y, and the task is to construct a pair of data, y hat and y tilde. This, I hope, using the rules defined on the y hat and y tilde to simulate the rules which is supervised with the choose x. All right, okay. So this is the first theorem. So suppose I consider Gaussian noise, and the noise has the covariance matrix sigma, and I can define pair which is very simple. One is plus a matrix multiply z, one is minus a matrix multiply z, and this z is normal distribution. Then, as long as these two matrices follows that A times B transpose is actually the covariance matrix, you can see the expectation of this error indeed is exactly the expectation of the error defined with the truth. This is really amazing because now you don't worry about whether you have X. You can just define such a pair. It can simulate very well the rules defined with the truth. For instance, if I consider this IID Gaussian white noise, I can set up one is just plus 1/2 z, the other one is minus 2z. Z is just the normal distribution. Okay, then you're done. So in other words, because now is expectation, right? I can simulate many pairs so that this expectation will be well approximated. That's result. And this R2 actually can be further extended to handle general noise. But the condition is that you have to know how to simulate the noise. All right. So suppose I have considered a very general noise independent, and I still can define a pair. The pair is still plus a noise, you minus the same noise. Okay. This noise is actually a random sample from the noise distribution. Then still have the same result. That is, the rules defined on this mean square error is actually the same as you define the mean square error over the truth. That's it. So in other words, there's no issue at all. You only have the noise measurement without truth. All right. Of course, then the training is that you just generate many such pairs just by using multiple examples from the noise distribution. Basically, you are done. Right. So this is very simple. Like you just need one line of the code, you get the job done, and it's correct. So if you look at the examples for image denoising, actually, you can see we are using the same network, same backbone as the DNCN, which is one representative denoising network, and this is our result. And you can see this error is in the second digits. All right. So in general, for this PSNR, actually people usually thinking the difference in the second digits is just nothing. So in some sense, the result from the R2R rules or from the rules which is supervised over the choose using the same network, they actually provide nearly the same performance. All right. So in other words, the noise is completely handled well by these R2R rules. Of course, you can also working on the real data. Here, you have to somehow have to model the noise distribution. The better noise distribution you can model, the better will be the result. All right. So of course, these R2R certainly is very powerful on handling measurement noise, right? And the denoising actually is one of the key part when you solve linear inverse problem. So here, let's consider solving a linear inverse problem y equal to ax plus n, right? So this problem can be decomposed as two tasks because any solution to this linear system can be expressed as two parts. One is XR, one is XN. The XR is X projected to the range space of A. And this XN is the X projected to the null space. That is AZ will equal to 0. Okay, so if you look at estimating the X from for the linear inverse problem, your task is you have two tasks, right? One is how to get XR, the other is how to get XN. So for the XR, actually you have the, if you could define the pseudo inverse, you actually know that you actually A pseudo inverse Y indeed is XR plus N. So from here you can see if you try to estimate XR, it's just a denoising problem. How to remove this N prime. All right. However, the things is different for the Xn, which is in the null space, X in the null space. And actually it's a solution ambiguity. Why? Because you can very easily verify Y is indeed can be expressed as A times XR. So which means XR and Xn are orthogonal to each other. In other words, Y contain nothing at all for the Xn. So you have two tasks. One is noise sensitivity for the XR. The other, this is a denoising problem. The other is the solution ambiguity, because you have nothing, you know nothing about Xn from the measurement Y. So of course, then the task for handle the noise sensitivity for the XR become very simple, right? You just extend this R2R based loops to the case where you contain this A. This is still hold true. So in other words, the XR can be handled very well by these R2R based loops, because you can completely remove the noise when you train the network. So, but solution ambiguity is not so easy to handle, right? So therefore, actually, this is not really a solution yet, but we just provide something working okay in practice. So the basic idea is that you treat it as a denoising problem using an intermediate estimator. So when you train the network, in each iteration, in each epoch, you're gonna have some intermediate estimator, just like we run an iterative solver, right? And this one, of course, you can treat it also as a denoising problem. It's just this noise is extremely difficult to know its property, because you have to know the truth, then you can know the property of N prime. Of course, we still can to, as we previous result state, right? We state that as long as you know the noise distribution, you can simulate such a noise, you can do the job by insert the same R2R loops, which means you're adding one noise in the input, you just subtract the same noise in the other one. Here the concern is that we really cannot get exact the prior for this noise, right? This is actually not the noise, it's a residual related to the truth. So here we actually do some hacking stuff. So basically we just empirically, we just randomly flip the sign of another residual, which is a prediction for the XT. Remember, XT is we use it as the intermediate estimator. Then we flip its sign randomly so that it's hope that it can simulate the residual N prime. Of course, it's not exactly true in theory, but somehow it works okay in practice. So here I give you one example. We evaluated this on the MRA reconstruction, which is solving a linear inverse problem. So you can see this scheme works pretty well because this MA MACnet is considered one of the state-of-the-art supervised learning method with train the network over like 100 medical image data, and this is our result without using any truth at all. And you can see some cases they are working better. Some cases ours are working better. This clearly shows that, I mean, the self-supervised learning can achieve the similar performance as supervised learning. That's important. Okay, so I'm done with half of my part. Another part is, remember here we somehow discussing the denoising problem and the linear inverse problem. This indeed is the linear inverse problem. How about nonlinear? because for the nonlinear problem, we cannot really get the exact like null space or the range space, right? Because operator is nonlinear. Go back to check again what exactly DNN can give us. So I still will go back to the sparsity prior, which have been the dominant approach before deep learning, right? So essentially, we know that the image itself is not sparse. You have to transform it to somewhere to make it sparse. If we think about a wavelet transform, basically X is not sparse, but if you transform the image into wavelet coefficient, the wavelet is sparse. Wavelet coefficient is sparse because many are colored in blue. Blue means it's close to zero, right? So in other words, if in the classical way, if you try to introduce such sparsity prior, you have to introduce some transform so that the X is no longer being like estimated directly. You estimate the C. So we call this reparametrization. You reparametrize this X using wavelet transform, and you try to estimate its coefficients now, not directly X. Right. So this transform can be defined or can be learned. For instance, like 10 years ago, not 10 years ago, like 8 years ago, we tried to see whether we can learn this wavelet transform to maximize the sparsity prior. However, with this deep learning things, actually, we show the ceiling of this kind of sparsity-driven image representation because you are using linear representation. I mean, it's certainly, its expression is limited. All right, so now we actually, with the deep learning, or especially deep neural network, we actually can move from the sparsity prior to the implicit deep priors. We'll come to this very soon. So the question you're asking is, what's the gain if you reparametrize an image using deep neural network? Certainly, you have two things. The first is it's a nonlinear form. Okay, for the nonlinear model, you can expect you can handle more complex structures in the image. All right. Second, we have the so-called deep image prior. I will come to this in next few slides. So it shows that by certain network architecture like convolutional neural network is actually implicitly will introduce some very useful regularization effect. Of course, you have a cost. What the cost is, if you try reparameterizing the image using a deep neural network, you have to deal with very large scale computation because the network will have millions of the weights. But here I have to clarify one thing that here I'm talking about deep neural network based reparameterization, which is not the generative model. Often people somehow will confuse about that. If you recall, what generative model is that the network is used as a mapping. So it can map a simple distribution like a normal distribution to the target complex image distribution, right? So the network weight is used to characterize this mapping. All right. However, when here I'm talking about deep neural network-based image representation, that this network weight is somehow acting like the coefficient. Okay, it's not like generative model. So in other words, I try to build up a map with zeta to the x. So one image, you have one set of the network weights. A different image will have different set of network weights. So it's more like acting the representation, not the mapping. That's the difference between DNN-based reparameterization and the generative model. So here is what I'm talking about, the deep image prior. Deep image prior, people realize that, discover that phenomenon that when you train a denoising network, you even though you don't have choose, and you start with some random seed, it will first show up the image structures, and more image structures will come in. Only passing certain stage, the noise will come in. So in other words, it will prefer the regular image structures than the random pattern when you train a neural network. So you can just call some early stopping, right, as a regularization strategy to get something out of it. All right, so but we have to decide one thing. If we want to think about this DNN-based reparameterization, we go for MAP or the MMSE. Actually, the MAP estimator was good for the sparsity-based prior. right? However, it's not good if you go on this deep learning based parameterization. Why? Because the first is F is not a one-to-one mapping. You have heavily over parameterization network. Secondly, F is a very complex non-convex function, right? As a result, it will be very challenging for the optimization because MAP is a point estimator. You try to hit that point, which with the deep learning, with the deep neural network, usually is very hard to get. All right, so from the perspective of the optimization, it's not wise to think things about MAP estimator. So that's why we're going to go to the MMSE estimator. MMSE estimator is that if you assume certain condition on F, we actually can re-express this conditional expectation as the expectation for the network weight beta. All right, this is super good. Now we only handle these network weights, try to get the conditional expectation. And here, of course, this can be calculated using, or have to some sense, calculated using Monte Carlo integration. And the whole point is how you can run the Monte Carlo or MC simulation to get this integral, because the beta is also living in a multi-million dimensional space, often like millions. Okay, that's the part. So okay, so in other words, if you try to realize this MS estimator using deep neural network based parameterization, the key is always about how to do the Monte Carlo sampling. All right, so here we just take the okay, we're just using what people actually have been widely know, that the fact that the longitudinal dynamics is a very effective MMSE estimate sampler for sampling the distribution in the context of deep neural network. So basically, this SGLD stochastic gradient longitudinal dynamic is built on this diffusion equation, and you have the Brown motion. If you express them out in the discrete scheme, you have this gradient descent together with this additional injection of Gaussian noise. So if we think about the context of inverse problem, right? This stochastic SGLD indeed is stochastic gradient descent we used for deep neural network training. Here, let's assume that the network weight follows a uniform distribution, and you only have a Gaussian white noise. Then I can write out this PDF pi zeta all the way go is actually indeed is only the fitting term you have, right? Nothing else. Then if you look at the stochastic gradient descent, you have the typical stochastic gradient descent, and its loss function is nothing, just the fitting term. And so difference is this artificially injected Gaussian noise. So this SGLD is just exactly the stochastic gradient descent we used for network training. It's just in the network training, we are using the mini batch to achieve this stochastic behavior. Here, we just assume you can inject Gaussian noise. And so, but here, as I said, this is sampling for multidimensional, right? It's very difficult. So we're using some heuristic approach. Basically, we know that if you want to target the truth, its cost function is actually variance. Okay, so in other words, which means if I just care about whether you can get a good estimator, not so care about whether it is true MMSE estimator, I can just only focus sampling in the area where its loose is close to sigma square. So I know the truth is somehow living in this omega, right? So we just focus on the sampling in this area, but it's just heuristic. So we have this so-called, you're just using some, when you inject noise, you just somehow using different step size. And the idea is that if you find out that this loss function is cost is less than sigma square, which means you have to decrease the function so that it can Oh, sorry. If the L theta is less than sigma square, which means you don't want to decrease its value again. So which means you try to inject a large noise so that it's more likely to go back to a larger L. This is opposite. If you know the L is larger than sigma square, which means you have to decrease the L to let it go to the omega, which means you have to reduce the magnitude of noise injection. So the idea is very simple, and the algorithm is also very simple. You just adding some strategy to make the step size is adaptive to the loss function value of the loss function, and you are done. Nothing else. You just adding one line, change one line in your code. Actually, you can make it over. So this is the application because because we don't deal with like null space or range space anymore, we can directly using this accord. So this is the result if we using it for the phase retrieval, and for the retrieval you have issues because you don't have choose, right? So most often when people using the deep learning, they are using plug and play. That is, you have some denoising network, some pre-trained model from somewhere else, and he just use it to deal with this target image, which often somehow has issue because the model you train, which might be whose corresponding data might not really reflect the data you want to process. So clearly you can see the proposed method achieves the best performance of all the cases. All right. And this is the one example, if you just visualize the data. So here is a traditional method, and you can see you have many kind of noise come here. It's not very clean. But if you use plug and play, the issue is that you actually will remove these small structures of these balls, right? And this is the truth. If you compare this one and this one, you can see many details are removed if you use plug and play. And here is our supervised. We actually provide better result in terms of noise because you don't see the noise, and the details are still preserved quite well. Okay, so I think I still have 2 minutes. I go to the next one. So we also talk about the bilinear inverse problem, which about image deblurring. So I will not go details. We actually handle a even harder case. We assume that the image is blurred in the different regions. So some regions you have blurred by this kernel, some regions you are blurred by another kernel. Anyway, you're gonna have such a model. Okay, you have to estimate both k and both x. This is a bilinear inverse problem, and so we still, because if you look at what tool we have the tool saying we can do the Monte Carlo simulation for estimating the expectation. Now it's become doable, right? That's the key. So if we go back to the like 4 years ago, actually, we actually discussed how to using another very famous static inference method called the variational EM method for blind deblurring. In that case, expectation maximization is a very classic method, right? So this is setting. We assume the data you have is the blur image. The latent variable is the latent image. What's the parameter is the kernel. That's actually a very suitable configuration to apply the EM for solving the blind deblurring problem. So for the EM, you have 2 steps. One is E step, one is M step. M step usually is okay as long as you really can calculate the expectation. This one is hard part. The key is how to do it, right? So in the classical form, so-called variational EM, people just using some Gaussian, especially using Gaussian function to approximate this part, make it solvable. Okay, we did the same. But in the self-supervised learning, we can give up on this. As I said, the key is how to calculate expectation. All right, expectation here. All right. So here, as we have the tool, right? So if we model again of the image using a network, model the kernel again by a neural network, we actually if we apply the EM algorithm, we still have E step and M step. The hard part is still the E step, right? But here, this looks complex, but the key message is that I'm using Monte Carlo simulation I just described for solving the general inverse problem to apply here. I just calculate expectation using the MC sampler, the MC samples. You are done. So this is the experimental result. You can see actually our method is doing very well. It actually can compete very well against even supervised learning method. Usually this this bolded font means the better result. So this is a demonstration, and this input, and you can see because it's taken at the nighttime, looks blurry, and this is supervised learning method, and this is our self-supervised. So without even using the tools, we actually can achieve a better result. So you can see, especially if you look at this this balloon, we actually has much clean and accurate estimation of the structure, as well as this building. Okay, that's all I want to say. I want to thank all the co-authors for all these papers. They actually the main driving force of all these works. Also, the code of the works I just discussed, you can check it out in the GitHub. All right, so that's all. Thank you.
Thanks a lot, Tiwei. Do you have questions from the audience? Thanks for the wonderful talk.
Thank you.
You can ask questions by unmuting yourself, or you can write them in the chat and you can read it. Right, so
I can ask something quickly.
Yeah.
Go ahead.
Hey, thanks. So you talked about map versus MMSE. I was kind of wondering if MMSE is kind of averaging over many samples over the posterior. I'm wondering if that can have a risk of like creating a blurry estimate.
No. If you have direct, because MMSE essentially is average. So if you have an estimator of the multiple images directly from all the way, you direct estimate the image and you take MMSE estimator, usually it will blurry. However, if now the difference that now you have a multiple estimator of the network weights. From the network weights, you get the images. Then you average them. They actually display the different behavior from the classic one. They don't show the such blurry effect. Indeed, okay. However, because since you are expert, I will say that now, because for the computational issue here, we only consider like 20,000. Okay. However, we show better performance. But if you allow to process a single image, train the image, usually we train it using like 3 to 4 minutes. But if you allow train the network to process a single image to generate sufficient amount of the samples, you actually can further increase the performance by a lot. So in some sense, we did not really solve the problem. That is, if you generate like billions of the samples, you actually produce a very good result. Just the computation will be very heavy.
Yeah, sure. Even 20,000 sounds like a lot, actually.
20,000 is very quick. Just a few minutes.
Yeah. Okay, that's nice. Yeah. Okay, thanks.
Okay.
Hi. Can I ask about this in the first part of the talk about this P here that you're trying to estimate here? So can you mention for real data, how do you do it again?
Which one?
This P here. So you need to know what
PN,
the
right?
yeah,
PPN. Okay. So actually we there's no like we just using some existing techniques. We are using a mixture of Gaussian to model the real world noise.
Okay.
Okay, so how to get the noise is people usually just pick up a flat area. Yeah. Suppose you have noise image, right? You pick up a flat area, then you get average, then you subtract average, you will get the noise. then you try to model this noise using mixture of Gaussian.
Ah, okay.
So we are not
That's
get
interesting.
exact P of n. We just somehow get P of n, which is hopefully it can approximate the real world.
Yeah. But this also suggests that, like, I guess, given that the results are very good, I think you might also say that, like, I'm not sure if it's true. Like, I'm wondering, you might actually say that the method itself is also like robust to misspecification of Pn. So, like, if you get Pn off a little bit, maybe it's still also okay. You think that's true?
Yes. So it certainly is true. Is that, but we don't have a quantitative metric to measuring like of course, I mean, if the noise you simulate is not really the noise of the measurement noise, the performance will decrease. But still, I mean, it does not give you negative impact. It still gives you bad result, just gain is not so much anymore.
Yeah, and it suggests that the results suggest it won't be too much of a problem. Okay, another question about the kernel thing, for the deblurring thing. So in an example, you had this deblurring kernel, like in this picture over here. I'm not sure if it's reasonable to assume that the kernel changes smoothly from location to location.
That certainly is true, because here actually it certainly is true. This we actually, for the blurring, you have two issues, two possibilities. One is the fast moving object in the scene. The other one is you don't have fast moving object. The scene is static. However, the blurring will caused by how far the object is away from you. So our model only work for the static scene. That is, you don't have the blur is not caused by the moving object, but caused by the motion, which will be impacted by how far the object is away from you. That model is okay. But if you consider the thing with moving object, this model is not right. So this model is only works for the static scene, not for the dynamic scene.
Okay.
Yeah.
Because I'm wondering, like, I mean, the fact that the kernel varies smoothly across space, can this be used as a prior or not?
You can. It's just how to characterize this kind of operation is not so trivial.
I don't know. Okay.
Yeah, it's not so trivial. We actually 10 years ago we have some related work which try to explore it, because you have to check in this orientation. You have to somehow make them have the same orientation. The orientation changes smoothly, and the kernel size changes smoothly. That one is hard to convert them to some differentiable functional. That's the issue.
Okay. Thanks. Any other questions from the audience?
Thank you, Hui. Very interesting talk. I have a question about the noise, similar to what Jonsson has, but your base model is additive white noise.
Yes.
It doesn't matter, no matter what the distribution is, that you can estimate using in the lower background part. What if the noise is signal dependent?
That's
like,
very good question.
Like the Poisson, and which is quite often generated in the medical imaging, like the PET imaging.
Poisson is okay, because Poisson is somehow very similar to, I say the noise is independent of signal. However, its variance can be signal dependent.
Okay,
in this case, actually, Poisson noise can be very well simulated by using Gaussian, but its variance change with the magnitude of the X. So
sure. That's
say,
what I mean by the signal dependent noise, is that its variance depending on the signal.
We actually can do that, handle it, but the issue we'll encounter is we don't know the exact covariance matrix. That's probably, of course, Poisson is kind of simpler, because we know it is somehow can be dependent on the magnitude.
Yeah, you're right.
Can I have a question?
Yeah, go ahead.
About like the your blur kernel. So is that possible? The blur image can be expressed with like a different combination, or like that will be like a. I mean,
so you
like
mean
so
you mean okay? So can I rephrase your question? Is can I cut this image into multiple pieces, each piece corresponding one kernel?
no, I mean like so the blur image will express by a set of blur kernels multiply convolution with like a clear image. So I mean, is that the solution will be unique, or like it can be expressed with multiple combinations?
I don't know actually answer question. There are two questions. Question is if I using this model, will this model will be unique in the sense that you have a unique K to characterize this Y. This one thing. The other thing is this what your question? The question is my answer is follows. It will depend on how rapid change of this kernel is. So basically, here you have implicit windows. So assumption of this model is that in the windows, the kernel is same or nearly the same. Here in the application, we'll set it as 8 times 8. If you have 8 times 8 windows, you have the same kernel. But in the case that for every pixel you have different kernel, that will go things widely.
Okay, thank you. Another one is, did you try to use like your self-supervised model to implement on like the segmentation or classification? Because I think a lot of self-supervised like learning, they just implement it as backbone to tackle those other tasks.
Okay, so what you're talking about is a different thing because the fundamental difference between the low-level process, what I did here, and the thing talking about the modality of the input and output change. Because for the application you're talking about, the output is no longer image, is some other type of data, right? Here but I'm not sure whether these techniques can be generalized to other modality because fundamentally your loss function is somehow self-supervised or just using the image itself. So if you want to attach
since you already have like a very
semantic meaning, go ahead.
I mean, like since you already have like a very excellent like backbone, so I think it will also achieve very good results for like those.
No, but the thing is, we don't have good backbone. We don't use because our result does not depend on the network architecture.
Okay.
As I mentioned, the thing is about design loss function. That's the key.
Yeah, I mean that will get you like a very good pre-trained parameters, right? Yeah, and then like I
know what you're talking about, but I don't know because for the application you're talking about will change the modality. So input and the output have different modalities that I'm not sure how at least we haven't really looked into it, but we might look into in future. Yeah, thank you.
Okay, thank you. Yeah.
All right. Do you have any more questions from the audience? If not, I think we can stop here. We can end the session formally.